Hey everyone, today we will be focusing on graphs today, particularly focusing on building a weighted graph, and without any further hesitation, let's get started. And now we are going to be focusing on creating a weighted graph. Now prior to, what I will be doing is that we are going to be creating a new header file in this case, because in order to create a weighted graph is really a type of graph that has connections based on different edges that have a different value associated with such. And for us to be able to replicate the behavior, we're going to create a new header file just for us, one, not to just get fully accustomed with the C++ syntax, but to also create the necessary behavior for our weighted graph. So in doing so, be sure to create a header file. I'm going to call this weighted graph right here. Yeah, it should be good. So this is our new header file called weighted graph, and what I will be doing is that first thing we always do is that we're going to include our libraries. We're going to have our class over here, and we're going to start filling out the class accordingly just within what we have. So our necessary libraries that we will need are going to be the following. We will include iOS stream. We will include vector. We will include list. Include CMath. Include unordered map. Include utility. Then include SSStream over here, and then we will be using namespace std. We're going to create a class called class weighted graph. And just like what we did with our graph printer, what we'll have a public instance. We're going to have void print graph constant vector indicate our list. Then we're going to pair with integers as well. So int, and this will put our adjacency list directly inside, so we can print out. And we're going to have constant over here. We're going to output our graph adjacency list, like we have done so over here. And down. And then we're going to have a for loop. Int v is equal to 0 for our vertices. V is less than the adjacency list size. When doing so, our iterator will actually increase. We represent it as v. We're going to output each vector that we have as v, and then we're going to have an arrow indicated for the direction of the following graph. And yes, you can have different combinations of graphs as well that would highlight their nature, just for reference. And then we're going to have a for auto loop or auto it for iterator, and we'll have our adjacency list with a vector on the inside. We'll start at the beginning, and then while the iterator does not equal to the end of the adjacency list, we will increment our iterator accordingly. We're going to output each parentheses here, right here for iterator first, here, iterator second. There we go. And this will be in the case for our following values that we will output for our weighted graph. Count and L. We'll have count and L. We're going to output our graph edges using ASCII and L, and render graph adjacency to be able to start. There we go. Then we're going to have a private class that we have that's going to render our graph. Private void render graph, constant vector list pair int. Yep, we've done so, and we'll have adjacency list as well. Constant will indicate for our radius, constant int radius equal 10, constant int diameter equal to 2 times radius plus 1, and then we'll have a vector strings to indicate the graph lines with diameter string for our diameter times 2, indicate for here, and int size is going to indicate the adjacency list's size that we will use whenever we are looping through our given values. And then I'm going to have a map, unordered map with key and value pairs, so indicating the actual integer values of what has been connected as well for our positions whenever we are given a series of values for our graph as well over what is connected and such. We're going to loop through by using a for loop for int I is equal to 0. This is how we initialize. I is less than the size, and then we increment I in this direction, so that way we go directly from the beginning to the end. We're going to have an angle. It's a double right here, 2.0 times m underscore pi times I divided by size. And then we're going to have int x equal radius plus static cast int radius times the cosine of the angle. Then we'll have int y equal radius plus static cast int radius times the sine for a following angle. And then we'll have our positions indicate based on the x and y axis. Positions at our following iterator indicated by x and y. And for int v is equal to 0, v is less than the size, while we increment each vertex, each of our following vertices accordingly throughout our adjacency list. We're going to have auto positions x and y equal positions of v, graph lines y x times 2 equal 0, and graph lines for y x times 2 plus 1 equal 0 plus v, and then for int v is equal to 0, v is less than the size, incrementing v accordingly. Then we're going to have another for loop for auto indicating the weights of our following edge, and then adjacency v for each following vector that we have. We're going to draw the arrow, so we're going to be calling upon a ladder function that like we did before. Void draw arrow. Just keep that right there. Arrow, graph lines, positions for V, positions for W, indicating for our expected two different vertices that we have. So V represents one, the first vertex, W represents the other one over which one is connected, and then we're going to have weights as another parameter to understand their nature and relationship from such. Then we'll have another for loop indicating for constant auto and line, graph lines, count, line, and L. There we go. We're going to draw arrow as well. Would draw arrow vector pair. Int from pair int. Two, since we're going to be doing from n2, and with our weight as well in each constant over here. Int x1 is going to be equal from first, then y1 is going to be equal to from dot second. Int x2 equal to dot first, y2 equal to dot second. Int distance of x is going to be equal to the absolute value of x2 minus x1, with also respective distance of y of the absolute value between y2 minus y1. This is why we have accordingly. Let me just put the spaces here. Int s of x is going to be x1, determining exactly the relationships between each respective vertex's distance between the x-axis and y-axis. We're going to have s of x equal x of 1 less than x of 2 for 1 for an edge case. We'll do the same thing for y. The slope accordingly. So here we have the distance. Here we have the following slope that we would need, given the fact that we're going to need different distances between such. And y, yep. And then error is going to be distance of x minus distance of y, overall between the two at its exact point. And then while we are scanning through everything, indicating it's true, if x of 1 is equal to x of 2 and y of 1 is equal to y of 2 in the respective vertices and the respective distances, we're going to break, and then we're going to have another distance calculated with e2 if e2 is greater than the y at a negative position. We're going to redeclare here error less than distance y, x1 plus equal s of x if e2 is less than d of x, error plus equal distance of x, y1 equal s of y if x1 doesn't equal x2 or y1 doesn't equal y2. We're going to have our respective graph lines, respective y1 x1 times 2 equal with outputting this part. So we have our edge case over here. Sorry if I misspelled that. If. Alright. Graph lines y2 x2 times 2 equal this. Place weight. Graph lines from to weight. And now we will have this function, place weight, placing the weight. So void place weight vector. All we can do right over here, we can literally do the exact same thing that we did before, except for the difference is that we will be placing the weight directly inside of a following graph line as well. Indicate exactly the significance of the weight between each of the lines. And we will have a string of vector of strings for our graph lines, indicating as a parameter, and then we're going to pair integers from, and then pair int to int weight constant over here, like we did before, up there. And then we could just do this part like what we did before. X and Y accordingly. X, Y, X, Y. And then int m of x is equal to x1 plus x2 divided by 2. And we do the same thing for y. String stream ss. This is going to indicate and differentiate between our following line versus our weight. And then we're going to have a string weight. Just like this is weight string, ss dot string up here, converting following integers into strings depending on where we're at. Then what I'm going to do is I'm going to have a for loop here. Int I is equal to 0, I is less than the weight. String dot size. Increment I accordingly. Then we'll have graph lines m of y, m of x times 2 plus I equal weight string at a following index as well. There we go. Make sure to also add this at the end, clean up all the necessary stuff. So we have a function to place the weight, we have a function to draw the arrow, we already have a function to draw, to render the graph and its radius, width, diameter. This can also be applied for cyclical versus acyclical, and this is where we print the graph. So overall, we have 4 functions whenever we print out the graph, and whenever we render our graph, draw the arrow, then place the necessary weight as well. So now, all we need to do, I'm going to head over to our main file. We always have an int main function whenever we are printing out stuff, and we're going to return 0. Oh, hang on. I meant to command B, build. Okay, build succeeded. And now we will be focusing on building our weighted graph and focus on our necessary problems now. And now we will be adding an edge to our weighted graph. So in order for us to actually get started, first thing I'm going to do is that we're going to include our libraries. And we also have our class as well, making sure we have a public instance at the same time inside of our class, so that way it can be called upon by different functions throughout our C++ main file. So the libraries I'm going to have included, there's going to be about 7. 1, 2, 3, 4, 5, 6, 7. We're going to have iOS stream. We will have vector, stack, queue, list, algorithm, and utility. And we will also include our header file, include weighted graph header file that we have over here. Then we're going to have our class in particular. I'm going to call, oh yes, and also don't forget using namespace std. Then we're going to have a class called the weighted graph class. Then we'll always have a public instance as well. In our public instance, we will have our variables, constructor, and necessary tasks we need to do. We need to add an edge, and we need to remove a vertex. We need to remove an edge, form, depth for search iteratively. Then we'll do the same thing recursively. Then we'll do the same thing for breadth first search as well. So the way we're going to initialize our variables is that a graph typically has vertices and our adjacency list as well. So vertices, we're going to go int v right up here. I'm just going to comment that as well. Then our adjacency list is really going to be a vector of it'll be indicated as a list for integers, or there will be a pair for such. We'll have adjacency here. Then we are going to have our constructor. So constructor is going to be called upon like this: weighted graph class for int v each vertex with respect to each connected vertex as well. And we will resize our adjacency list based on the number of vectors that we have as well. And now for our function to add an edge. So what we will be doing to add an edge is we'll go void add edge int v int w int wt, because for a weighted graph we typically have a number that is associated with each connection for each vertexes respectively, such as down here before. So I'm going to have adjacency v dot pushback for make pair. We'll have w and wt as well, making sure we have our parentheses already set up in place. Let me just, there we go, that's better. Then we'll do the same thing for w, and I'll just basically just keep everything clean. So w, we replace this with v as well, with the respective connections as well. Now I'm going to head over to our main function as well, so we can actually print this whole thing out. And the way we go about this will be the following: we'll have weighted graph class. We're going to call this graph 6, and we'll have graph 2, 3, 4, 5, 6. We're going to call upon this function as well by using dot add edge. And notice in particular when we add edge, we have 3 different variables that we can add. So we have a vertex v, vertex w, and a weighted graph number as well. So we can do add edge as well. For following, I'm just going to do the same thing for the other one. Edge. Second. Int v. So since we have integers, what I'm going to be doing is 0, 1, and 4. Then I'm going to have 1, 2, and 3. You can space them out just to clean it up. Then you're going to have 2, 3, and 2. 3, 4, and 6. Then 4, 5, and 5. Finally, 5, 0, and 7. Then I'm going to call upon our header file by doing weighted graph. I'll call this printer. And then I'm going to have printer dot here. Sorry about that, folks. Printer dot print graph for graph dot adjacency list. Since we're printing out a whole list of what we added, let me just build this, make sure everything's good. Build succeeded. And now we have our weighted graph accordingly. Let me just zoom out of that. Okay, yes, so our weighted graph is already set up accordingly. So we have our adjacency list that we have already built. We see the connections between each of the vertices and their respected weighted graph. So we, for instance, would have, for 0, we have 1 and 5 as well. And then we also have the same for 1. We see its connection between 0 and 2 with its respective weighted graph number at the same time. And we see this accordingly within our relationship that we have set up in place over here. And this is what our weighted graph would look like when we added the edge. Now, let's head over and focus on removing a vertex from our weighted graph. And now when we remove a vertex, we are going to be doing the following, is that all we need to do is do void remove vertex for our instance of v as a parameter, and then we're going to have this for loop that's going to run through our adjacency list for auto and neighbors, adjacency. We'll have neighbors dot remove. Actually, we're going to do this thing called remove if. And since we have a weighted graph that is associated with an edge, this is why we do a remove if. We'll have a v for its respective pair as well. Int and edge at the same time. When in doing so, we are going to return an edge, very first instance, with its respective vertex as well, because we have a number associated with its own respective edge as well. There we go, that should clear it up. And I'm just going to have adjacency vector dot clear, which will clear up everything, make sure it's all good, build succeeded, and now we're going to head over to our main function to be able to remove this accordingly. So what we will do is that we are going to have graph dot remove vertex, like we did before. We're calling upon this function, and with specifically, let's go with removing the third vertex that we have. So I'm just going to output graph after removing vertex 3, then NL, then printer dot print graph dot adjacency. Go. Build this. Build succeeded, and we're going to run this again, see how well it did, and looks like it actually removed the vertex from the following graph as well, and its respective edges as well, since we need to fully isolate it and go through it accordingly. So this is what our graph looks like. Let me just zoom out of it so you folks get a better look. This is what we did. All we did was that we used a for auto loop, and then we used remove if because we have a vertex already paired up with a respective weight with its edge, since we need to isolate the vertex as well. And now let's focus on removing an edge within our weighted graph. And now we will focus on removing an edge for our weighted graph. So the way we are going to be going about this is for the following. We're going to do void remove edge int v int w, and we're going to have our adjacency list with respect to our vertex for v, and then we will also do the same thing for w, so adjacency with w for second vertex, and then we will use remove if like we did before for our remove vertex. And this time, for our context, since we are doing this in respect to each vertex, what we will be doing is that we will be doing the same thing that we did up here before, except we're going to be focusing on the edge in general. So that means for v, that means we go with w, and this means we also go with w as well. We can also do the same thing for the one at the bottom. Make sure you have your semicolons already set up. Then we can do the same thing for the following over here. So we just place this with v. Also do this with v because we're removing an edge with its respective weight as well. There we go.
Passengers with flight 5269 to Philadelphia, our aircraft is on the ground and headed into the gate. Our ramp does look like it is back open as of right now, seeing as though the DFW flight.
The next part that we will be doing
so as long as we don't see any
is that we will just call upon
so they can pull in our aircraft. Right now, ramp looks like it is open. They brought in that one, so we're just going to pray that the flight doesn't start again, because they'll have to close for another 5 minutes until the lightning has passed.
Dot remove edge.
For them to be on the ramp at that time.
So for 2, and then 3, and then count graph after removing edge 2 and 3, and L. I'm going to do printer dot print graph as well for our respective adjacency list. We're going to build. Make sure everything is already set up in place. Now I am going to run this. And we have removed our edge successfully between 2 and 3. And we have also shown our following graph as well. Notice in particular for our adjacency list, and then also for our following graph at the same time with those respective weights. And now we will perform depth first search iteratively for our weighted graph. You will be noticing some similar designs and sequences that we have already typed out thus far in our course. And the way we're going to perform depth first search iteratively is going to be the following. So first thing we're going to do, we're going to have a function void DFS iterative, and I'm going to have a parameter int v. And what we will be doing is that we're going to move a vector of booleans to determine what has been visited and what has been visited within our adjacency list, just like we did before with respect to our vertex that we have. Each vertex that we have initialized, we are initializing it saying that we haven't visited anything yet, and then since depth first search uses a stack, we're going to have a stack of integers. Unlike breadth first search uses queues. Depth first search uses stacks. We're going to push each vertex that we see into the stack, and while the stack is not empty, we're going to check the top of the stack, because stacks can be thought of as a stack of plates. We're going to pop the stack to be able to output what has been visited and what hasn't. And if a vertex has not been visited, hence the exclamation part, this part indicates saying not visited. Not visited a specific vertex. While we're going through our adjacency list, we're going to output each vertex indicating that it has been visited, and we will indicate that visited for v over here is going to be indicated as true, since we have a boolean in this case and we need to determine what has been visited, what has not been visited. And while doing so, we're going to use auto I. We're using a auto for loop indicating for the adjacency list at the beginning, so our beginning, meaning since we have a stack, we're using it at the top of the stack until we reach the very bottom at the end. So that means our index, while our index doesn't equal, at the end of the stack, indicated as our end, keep incrementing our index, and we will indicate each following vertex that we see and push it inside the stack. So that means we're going to have a visit. If a vertex has not been visited with respect to their edge, so we will have first in this case, and then we're going to push our vertex with their respective edge since we have a weighted graph. So we're going to I first. There we go. Just make sure everything is right, and then I'm going to perform count and L. Make sure everything is already set up in place. Make sure you have your equal sign as well. Apologies on that. Well, it doesn't equal. There we go. That should work. Apologies on that. Make sure that you have everything already set up in place. Here. So this looks good in terms of iterative depth first search. Now what I'm going to be doing, I'm going to go into our main function that I have. In fact, we're going to put this right here. And our following depth first search, since depth first search goes based on the depth of the following graph, we're just going to output depth first search iterative, starting from vertex 0 there we go, and I'm going to have graph.depth first search iterative with starting at 0, since we have indicated that we're following vertex as well. Indicated for 0. Now I'm going to build, make sure it's all good. Build succeeded, and we're going to run this. And our depth first search for the following goes in this case. So we know exactly what has already been connected. Hang on. Apologies on this front. we need to do this right here because we need to add edges to the graph. There we go. Starting from vertex 0, so we have 0, 1, 2, 3, 4, and 5. Since really this is all connected based on a weighted graph's edges as well, we notice in particular on how the vertices are already well connected based inside of the weighted graph. But in terms of depth first search as usual, based on principle, goes based on the depth of the graph. I also have an infographic to be able to showcase the nature of a weighted graph and how depth first search is also conducted, and this is the reason why we get the following outputs over here. And so yes, this was depth first search built out iteratively. Now let's head over and focus on building depth first search recursively. And now we're going to perform depth first search recursively. So the way we're going to do this is that we always know that depth first search typically has calling upon the principle of recursion. Typically has two functions in this case, where we have our helper function, then actual function that we call. So our helper function is going to be built out based on the following: void depth first search recursive with int v, and then we're going to have a vector of booleans to indicate what has been visited. And then for each visited vertex, we're going to indicate this one as true. So it's a unique way of actually writing out sort of like a Boolean condition, in this case, to determine what has been visited while we're scanning throughout our adjacency list. And then we're going to output each vertex that we have visited for true. And we're going to have a for auto loop to scan through our adjacency list. So for auto I is equal to adjacency reach vector at the beginning, and while I does not equal adjacency list at the end, we're going to keep iterating through the adjacency list, and our index will continue to increase. And then if our following vertex has not been visited with respective to the edge, so I first, since we are dealing with a weighted graph, we're going to call upon the function again to then loop around until everything has been visited. So I first, and then visited. Yeah, there we go. Then we're going to have our actual function, which we call upon. And be sure. Oh, okay. Sorry about that. Just make sure that your brackets are actually already lined up. There we go.
Please pick up the white courtesy phone and dial 0 for a message.
Then we're going to have our actual function we're going to call. So we're going to have DFS recursive at the start, int v, and then we're going to have a vector of booleans to indicate what has been visited, initializing with our vertices that we have initialized at the top here. Put that together. There we go. Pick this up. Going down. There we go. Visited, and then we initialize this as false since we have not visited anything. And this is how we initialize our vector of booleans. Then we're going to call upon our helper function here, DFS recursive for v, indicating what has been visited. And then we're going to output until we reach the very end of our adjacency list. I'm going to build this, make sure it's all clean. Build has succeeded. I'm going to go all the way down the main function after we've added the edges. Now we're going to do this recursively. So basically we'll just do the same thing that we did. Just call this recursive. Instead of doing graph.dfs iterative, we're going to have dfs recursive at the start in this case, and we're going to do this at vertex 0. So let me just build this out, make sure it's all good. Looks like the build has succeeded. Should get the similar result, and we did accordingly. So this was depth first search in a recursive matter. We still got the same result as we did for iterative. We just built it out differently using principles of recursion and not just iterative. So this is how we built out depth first search from a recursive perspective. Really, I can zoom in further. There we go. So that way you can see exactly how we already built this out and got our desired output. Now, let's head over and build out breadth first search iteratively. And now we're going to perform breadth first search iteratively. Now, in order for us to do so, first thing we're going to do, we're going to call upon by using void breadth first search iterative, and then include our parameter int v. And then what we're going to do, similar to what we did before for our depth first search, except for differences, is that breadth first searches always use a queue. Unlike depth first searches use a stack. So we can technically apply some of the principles that we have already done beforehand, except for the differences is that we will be using a queue in this case. So, and understanding the natures of queues go first in, first out. Yeah. While stacks go last in, first out. So some principles that we can actually take, we can use the vector of booleans that we have already made in particular, and this time we're going to use a queue of integers, indicate that as queue, and we're going to indicate what has been visited and set the first vertex indicated as true, saying, hey, we've already visited, and we are going to push each vertex that we have visited inside of our queue currently. And while the queue is not empty, we're going to push what we have done and see each vertex and put it at the front. So V right here, and then we're going to pop the queue accordingly and do a for auto loop, except for differences is that we're not going to use r begin or r end like we did for our stack inside of depth first search. We're going to instead just use begin and end for our queue. So for auto I is going to be equal to adjacent v at the beginning, while the index does not equal the vertex at the end of the adjacency list. We're going to still increment our index until we get to the very end of our queue, and that means if the visited vertex with its respective edge I all the way to first has not been visited, that means visited I's first weighted, would indicate that as true. Then we're going to keep pushing each index with its respective vertex and its edge by using first as well. Then we will go over here, make sure that we're spelling everything correctly. There we go. Count and L. And so far everything looks good. Let me just build this out, make sure that it's good. Build succeeded. Okay. Now I'm going to head over here, and similar to what we did for depth first search, except for we're going to be using breadth first search. So BFS iteratively starting from vertex 0, and instead of DFS iterative, I'm just going to go BFS iterative, and we're going to start at 0. I'm going to build this, make sure it's all good. Build succeeded. Perfect. I'm going to run this, and we get the following output that we have over here for breadth first search. Since breadth first searches goes based on levels, while depth first search goes based on depth, which is why we get our respective output in this case, understanding in particular the differences between breadth first search and depth first search overall. I also have a following infographic to explain and showcase. Now, this is how we build breadth first search iteratively. Now, let's head over and focus on building breadth first search recursively. And now we're going to perform breadth first search recursively. So the way we're going to go about this is that we always need to keep in mind and remember that recursion is really building upon a function inside of a function. So that means we're going to have two functions. Excuse me. We're going to have our helper function, and then we're going to have our function we actually call upon. So the way we're going to build our helper function will be the following. So void BFS recursive. This time, since breadth first search uses a queue, we're going to go queue int and queue with vector with boolean, and we're indicating what has been visited. Then we are going to see, in the case where if the queue is empty, that means we're just going to return nothing altogether because we have not added anything inside of the queue. And then we're going to initialize our first vertex to be at the front of the queue, since queues operate based on first in, first out. Then we're going to pop the queue accordingly, and we're going to output each vertex with their respective space that we have. Then we're going to have a for auto loop. For auto I equals adjacency v at the beginning, while I does not equal to the adjacency vector or adjacency list with the respective vertex at the very end. We're going to increment our index accordingly. Then, since we are dealing with weighted graph, we're going to have to use first. So if the following vertex has not been visited, because it's a Boolean condition, then we're going to have in the context as well for the respective edge of index first, indicating for the weight of the given edge. There we go. Then we will be pushing each index and the respective weighted edge to indicate that we have visited once we have already reached it. Then we're going to push it inside of our queue with I first is really just the edge. Then we will be doing this until we have reached the end of our adjacency list. So BFS recursive, yes. That means with queue, and then we will have visited as well. So we're using parameters inside of parameters to be able to run around until we actually reach to the end of our final queue. Then we're going to have our function that we actually call upon in our main function. So it's going to be void graph first search recursive at the very start with int v indicated as a single vertex, and then we're going to have a vector of booleans to indicate what has been visited, and with our vertex that we have initialized at the very top right here, along with the vector list that we made for our adjacency list over here, back down. We're also going to indicate false since we have not visited anything. Then we're going to initialize a queue with integer and another queue right here. Then we will indicate what has been visited at a specific vertex to indicate that this is true, and then we're going to push our vertex inside of the queue to indicate that it has been visited. Then we're going to call upon our helper function inside of our actual function, then put it in queue, and then also visit it from here. Then finally output all the way to the end of our adjacency list. Now, we're going to do the exact same thing we did for depth first search, except for we're going to do this for breadth first search. So BFS recursive starting at vertex 0. That means in particular we will have breadth first search recursive at the very start, and this time we're going to have 0 in that case. Let's build and make sure everything's already lined up. Build succeeded. Let's run this, and we get our expected output that we need for breadth first search as well. Now all we did was just implement a different method for how we actually built out breadth first search using principles of recursion, unlike our iterative approach where we just use the queue and checked whether each vertex would be called upon whenever we visited, and pushed it inside of our queue with their respective weighted edge as well. So we know exactly in particular over what is being added inside of our queue, and then finally outputting our following edges as well. Now let's go over a brief overview for what we have already accomplished for our weighted graph. And now going over our whole weighted graph experience. So our weighted graph in particular, we made our own custom header file really to be able to go over exactly how we were able to build out our weighted graph with the respective values that we see whenever we are outputting. For each value is going to have a specific for each edge is going to have a specific value that is attached with each of the vertices that are connected with the respective edges as well. And we need to replicate of that nature by rendering the graph first, then we draw the arrow depending on exactly if this is actually a directed or undirected graph. In our case, arrows really do indicate that it is directed overall, just for this example. And then we place the weight, which will be directly on the inside, and we did this with ASCIIR as well, just to be able to output and know the direction of what we have done, plus also get further accustomed with the C++ syntax at the same time. So we did 1, 2, 3 functions along with our print graph function as well. So we did 3 private functions and 1 public function in general. Then inside of our main class, what we did, main file, is that we included our following libraries. Then we had a class called Weighted Graphs. We made a public instance so that way we can call upon what would be needed inside of our main function at the bottom. And what we did was that we initialized the variables for vertices as well as our adjacency list for graphs it's a way to actually organize our following vertices and with their respective edges and understand the relationships with such. Then we have our constructor called Weighted Graph class that we call upon inside of our main function to then add edges and then call upon other functions that we have built out accordingly throughout our entire class. So we have gone through the problem of adding an edge. Then we also focus on removing a vertex. Then we focus on removing an edge, as we have seen in our following examples we have had done. So that's the vertex removed. This is an edge removed with the respective weight also removed. We performed depth first search iteratively, and then we have also performed depth first search recursively as well. We see the following values that we have already outputted, and then we also have performed breadth first search iteratively in this pattern, and then we've also performed, sorry about that. There we go. So this is breadth first search iteratively. Then we performed breadth first search recursively, knowing even though we got the similar output, well, the exact same output, we just built out breadth first search print and depth first search based on different principles of iterative and then recursion as well. And this is what we output for our main function as well. The following links are also within our GitHub repository in the description below, so you can go back, look at references, and then be able to check back on your work while you're typing out everything and coding along side by side at the same time. So yes, this was our weighted graph that we have built for our vivid example. And yeah, now let's head over and focus on the principles of understanding an unweighted graph and how it's already applied within the different types of graph problems that we have already been working on and working towards throughout the rest of this course. So let me just move this. There we go. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.